transport layer breaks the stream into segments of data that it reliably delivers to an application running on another computer. The transport layer sends these segments as network layer packets, which the network layer delivers to the other computer. Let's see what this looks like in practice, the actual packets that a web browser and server send and receive. First, let's look at the transport layer. Almost all web traffic is over TCP, the Transport Control Protocol. In its typical operation, there's a client and a server. A server listens for connection requests. To open a connection, a client issues a connection request which the server responds to. I won't go into the details of exactly how this works, but it turns out this exchange takes 3 messages, something called the three-way handshake. The first step of the message is when the client sends a synchronized message to the server, often called a SYN. The second step is when the server responds with a synchronized message that also acknowledges the client's synchronize, or a synchronize and acknowledge message, often called a SYN-ACK. The third and final step is when the client responds by acknowledging the server's synchronize, often called an ACK. So often the three-way handshake is described as synchronize, synchronize and acknowledge, acknowledge, or SYN, SYN-ACK, ACK. Recall that the network layer is responsible for delivering packets to computers. The transport layer is responsible for delivering data to applications. From the perspective of the network layer, packets sent to different applications on the same computer look the same. This means that to open a TCP stream to another program, we need 2 addresses. The first, an Internet Protocol address, is the address the network layer uses to deliver packets to the computer. The second, the TCP port, tells the computer software which application to deliver data to. Web servers usually run on TCP port 80. So when we open a connection to a web server, we send IP packets to the computer running the web server, whose destination address is that computer's IP address. Those IP packets have TCP segments whose destination port is 80. But how do those IP packets get to their destination? We don't have a direct wire connecting my client to the server. Instead, my client is connected to an intermediate computer, a router. This router is itself connected to other routers. IP packets between the client and the server take many hops, where a hop is a link connecting 2 routers. Since my client is on a Wi-Fi network, the first hop is wireless to the Wi-Fi access point. The access point has a wired connection to the broader internet, so it forwards my client's packets along this wired hop. A router can have many links connecting it. As each packet arrives, a router decides which of its links to send it out on. Routers have IP addresses, so it's also the case that it might not forward a packet, but rather deliver it to its own software. For example, when you log into a router using TCP, the IP packets are destined to the router's own IP address. How does a router make this decision? It does so through something called a forwarding table, shown here on the right. A forwarding table consists of a set of IP address patterns and the link to send it across for each pattern. When a packet arrives, the router checks which forwarding table entry's pattern best matches the packet. It forwards the packet along that entry's link. Generally, best means the most specific match. I'll describe how matching works in more detail in the video on longest prefix match. But in this simple example, let's just consider the default route, the first entry in the table above. The default route is the least specific route. It matches every IP address. If, when a packet arrives, there isn't a more specific route than the default route, the router will just use the default one. The default route is especially useful in edge networks. Say, for example, you're Stanford University and have a router connecting you to the larger internet. Your router will have many specific routes for the IP addresses of Stanford's networks. Send packets to the engineering school over this link. Send packets to the library over that link. But if the destination IP address isn't Stanford's, then the router should send it out to the larger internet. So now, let's look at some IP packets in a real network. I'm going to request a web page from www.brown.edu and use a tool called Wireshark to show you all of the packets. We'll see how my web browser opens a TCP connection to the Brown web server using a three-way handshake of SYN, SYN-ACK, ACK, then starts issuing HTTP GET requests which the server responds to with data. Once we've seen the exchange of packets between my client and the Brown University web server, I'll use another tool called traceroute to observe the path that these packets take through the internet. So first, I'll start up Wireshark. Because my computer is using many network applications and sending lots of different packets, I'm going to tell Wireshark to only display packets that are TCP segments to the Brown server using port 80. This way, we'll only see the web traffic I'm generating. I'm also going to tell Wireshark to listen on EN1, which is the name my Mac gives to my Wi-Fi link layer. As you can see, I have many link layers available, but let's just look at EN1 since that's how I'm connected to the internet. Next, I'll open my web browser and request the web page for Brown University's Computer Science Department. This is where I went as an undergraduate, and so I like to keep up with news in the department. You can see in Wireshark that loading this page involves sending and receiving a lot of packets. Wireshark shows me the timestamp of each packet, the source IP address, the destination IP address, what protocol it uses, its length, and further information. Let's look at this first packet. It's from my computer, whose address is 192.168.0.106, to the Brown CS web server, whose address is 128.148.32.12. It's going to TCP port 80, the hypertext transfer protocol port on the server, which we can see from the HTTP field in the info column. The packet is a SYN packet, the first step of the three-way handshake. Look at these first three packets. The first is a SYN from my computer to the web server. The second is a SYN-ACK packet from the web server back to my computer. The third is an ACK from my computer back to the web server. This is the three-way handshake. Now the two computers can exchange data. And you can see that the first data packet is an HTTP request. My computer sends a GET request to the web server. The response to this GET request is 3 packets. Wireshark shows the response when it receives the third one, shown on the line whose info is http:/1.1 OK. So here we can see how my requesting a web page from Brown's computer science server creates a TCP connection to the three IP packets for the three-way handshake, then more packets for the HTTP request and response. This is how the network looks to the end hosts, the computers, as they exchange packets of the network layer. But how does it look like inside the network layer? What hops these packets take? To see this, I'm going to use the second tool, traceroute. Traceroute shows you the hops that packets take to a destination. So we can type traceroute www.cs.brown.edu to see the path through the internet. I'll add the -w flag, which specifies a timeout with a timeout of 1 second. The first hop the packets take is to my wireless router, whose IP address is 192.168.0.1. As you can see from the next hop, I'm at home. I have a cable modem, and my internet provider is Astound. After this, packets take another hop to an IP router with IP address 74.14.0.3. The hop after that is a router in San Francisco, California, then several routers in San Jose, SJC for above.net, and San Jose 1 for level 3.net. After San Jose 1.level3.net, the packets are across the United States and New York. They go through a series of routers in New York, EBR, CSW, EBR, then on hop 13 to Boston. Boston is very close to Providence, where Brown is. After ocean.org, we see 3 stars. This means there's a router that won't tell traceroute about itself. The stars are traceroute's way to show it waited for a reply, but the reply timed out. On hop 20, we see a router in Brown's CS department. After that, everything is hidden. Brown's CS department doesn't want you to be able to see what the inside of its network looks like. Because we couldn't see the path end with Brown's web server, let's try another one, the Computer Science and Artificial Intelligence Lab CSAIL at MIT. We can see that packets take the same path to Boston until hop 15. The path to Brown goes to Ocean at hop 15, while the path to MIT continues in level 3's network. On the path to www.csail.mit.edu, only 2 routers are hidden, the 13th and 19th hops. We can see that www.csail.mit.edu is also named acron.csail.mit.edu, and, after 22 hops, packets from my computer reach MIT's web server. Look at the time values. The time from my packet to reach the MIT web server and its response to return to me, there and back, the round trip time, is under 90 milliseconds, or less than an eye blink. We've now seen the life of a packet, starting as an application-level client web request and taking nearly 20 hops through the internet to reach its destination. For me, this is one of the best things about teaching this course. Everything we present is something that you and I interact with every day, even just in the space of watching one video. It's easy to see the principles and ideas in practice, and with just a few simple tools, you can inspect the internet in operation in real time.